A doubly linked list is a dynamic data structure that extends the concept of a singly linked list by allowing bidirectional traversal through a sequence of nodes. Each node in a doubly linked list contains three components: a data field that stores the actual value, a pointer to the next node, and another pointer to the previous node. This bidirectional linking results in a more flexible and powerful structure compared to singly linked lists, enabling efficient operations from both ends of the list and easier deletion or insertion at any position. A doubly linked list starts with a pointer known as the head, which points to the first node, and often maintains a tail pointer pointing to the last node for faster back-end operations. The last node's next pointer is null, while the first node's previous pointer is null, because each node stores two pointers instead of one. The memory overhead is higher than in singly linked lists, but this additional cost is justified by faster operations and improved navigational capabilities. The biggest advantage of a doubly linked list is its ability to traverse forward and backward, making certain operations more efficient. For example, if only the last node is known, deletion or insertion at the end is quick and avoids traversing the entire list. In a singly linked list, deleting the last node requires traversing from the head to the node before the last. But in a doubly linked list, having immediate access to the previous pointer simplifies this operation dramatically. This property also makes doubly linked lists ideal for implementing data structures such as DQs, browser history navigation, forward and backward, MRU, LRU caches, and navigation in media players where both previous and next options are required. Doubly linked lists are built using dynamic memory allocation, typically through the use of malloc in C programming. Each time a new element must be added, memory is allocated for a node. The data is stored, and the pointers are adjusted. Insertion operations vary depending on where the new node must be placed. Inserting at the beginning requires assigning the new node's next pointer to the current head and setting the previous pointer of the old head to the new node. The head pointer is then updated. Inserting at the end requires a traversal to the last node unless a tail pointer is maintained, after which the last node's next pointer is assigned to the new node, and the new node's previous pointer is set accordingly. Insertion at a specific position requires finding the appropriate node, linking the new node between the previous and next nodes, and adjusting their pointers to maintain list integrity. Deletion operations in doubly linked lists are more efficient than in singly linked lists because nodes have direct access to both neighbors. Deleting the first node simply involves moving the head pointer to the next node and setting its previous pointer to null. Deleting the last node involves updating the previous node's next pointer to null. Deleting from the middle is easier than in singly linked lists because the node can be removed by connecting its previous pointer to its next pointer without needing to traverse backwards. After adjustments, the deleted node's memory must be freed to avoid memory leaks. Traversal is also more flexible because the list can be navigated in both directions. Forward traversal begins from the head and continues until the next pointer becomes null. And backward traversal begins from the tail and continues until the previous pointer becomes null. This dual direction capability makes doubly linked lists ideal for algorithms that frequently require backward movement or bidirectional searches. The applications of doubly linked lists are numerous and significant in computer science. They are widely used in implementing advanced data structures like Fibonacci heaps, navigation systems, and complex memory management schemes. In operating systems, process scheduling queues often use doubly linked lists to allow quick removal of nodes without full traversal. Many programming languages use them internally for implementing their standard libraries, such as the list container in C++STL or the linked list class in Java. They are also employed in undo-redo mechanisms, where each action can be navigated to the next or previous state. MRU and LRU caches rely on doubly linked lists combined with hash tables for efficient storage and quick updates. In database systems, they are used for maintaining index structures and optimizing storage of large records. Despite their strengths, doubly linked lists also have drawbacks. They require more memory since each node stores 2 pointers, which increases overhead especially for large datasets. Furthermore, operations require careful pointer handling, and errors such as forgetting to update one pointer or incorrectly adjusting predecessor and successor pointers can easily corrupt the entire list. Dynamic memory allocation and delocation need special care to avoid memory leaks or dangling pointers. Additionally, while traversal is flexible, random access remains inefficient since elements must still be reached sequentially from either end, resulting in a time complexity of O(n) for accessing a specific index. In performance terms, doubly linked lists provide constant time insertion and deletion at known positions, which makes them ideal for applications with frequent modifications. Their ability to adapt to memory fragmentation is valuable in systems with limited or scattered memory availability. Despite the rise of modern data structures, doubly linked lists remain crucial in understanding fundamental concepts of data organization, pointers, memory management, and linked data structures. They serve as a stepping stone to learning more advanced structures like skip lists, balanced trees, and graph representations. Mastering doubly linked lists strengthens a programmer's understanding of how data structures behave at the system level, sharpening skills essential for low-level programming, embedded systems, and algorithm design. Overall, the doubly linked list is a robust, versatile, and foundational data structure whose advantages in dynamic behavior, bidirectional navigation, and efficient modification operations ensure its continued relevance in both theoretical learning and practical applications across numerous domains.